The quadric sections that we've just been talking about are not exactly functions. The functions have to be expressed as z equals to some function of x and y without the z. Otherwise, it's called an implicit function. So, for example, we have the last thing we did on our way out was the cone, which I didn't really get to talk much about. But if we take a look at the cone is expressed as z squared is equal to x squared plus y squared. So what you could do is you can add a variety of things to this program. First of all, maybe I want to uncheck this so it doesn't draw this function that I don't need. I'll ask it to graph again, so now there's nothing there. And then I'll go to graph, and I can draw a vector, a space curve, which is what we're going to talk about today, a vector field, that's chapter 16, a region, parametric surface, and an implicit surface. So the quadric sections can be expressed as implicit surfaces. So when you say yes to this, you are essentially going to enter an equation, something equal to something, that involves an x, a y, and a z. So we can type in, I think it was x squared plus y squared minus z squared is equal to 0. But I'm going to write it this time a little bit differently. I'll say z squared is equal to x squared plus y squared. And you have to use the primitive, that's not primitive, the caret for the exponent. And then you can graph this to get some idea of how this thing might look like. The neat thing about this is that you can view this from different angles. And then if you have little or no control of your mouse and you can't get it set, I think you can always just reset and then graph it again. Okay? Yeah?
You can handle fractions and complicated numbers, right? It's pretty easy, like, or do you have to enter a bunch of parentheses and stuff? You know what I'm talking about? Or
No.
never mind. Don't worry about it.
Yeah. Yes, it can handle more than one function. So right now, implicit surface number 1, it says here in my window. I can throw in another implicit surface, like go to graph again, implicit surface. Well, I could throw in a different thing, but let's throw in another implicit surface. And, okay, can you guys look at this graph? It says x squared minus y squared plus z squared is equal to 2. Let's go through the thought process of all the quadric sections that we've learned. First of all, does this look like well, I'm just going to ask the questions first. So some thought process that might go through. What are the signs? Well, first of all, are there any differences in the radial distance along the x, along the y, or along the z? So there's no big differences like that. Okay, so the other thing to look at is, are all of the x, y, z squared? They're all squared. So I know it's not a paraboloid. So far I've only eliminated the paraboloid. So let's look at the sign, positive or negative. Are all the x's, y's, and z's, are they all positive? If they were all positive, then this has a chance of being an ellipse or a sphere. All right? You guys said no to that. So it's not an ellipse or a sphere. It's not a paraboloid. And so what's our last? It's not an ellipsoid or a sphere, and it's not a paraboloid. So what do we have left? Hyperboloid. So now it's a question of hyperboloid or one or two sheets. So why is it one sheet? Because what? It's not equal to 0. We could bring the 2 over to the other side. It would be equal to 0. It's what? There's only one negative in the variable, right? There's only one negative in the variable. If you have 2 negatives in the variable, then there's a good chance this is hyperboloid of 2 sheets. There's only one negative, so it's hyperboloid on 1 sheet. Now, this is not our first example of a hyperboloid of 1 sheet. You have to look at which one has the different sign. So the y has a different sign. So what can you say about the xz versus the y? How is this hyperboloid going to look like in your drawing? So a hyperboloid is like they have a picture in the book of like those what do you call those? Not the saddle. The nuclear plants, the silos, yeah. The silos for the nuclear plants are shaped like kind of like a 1 sheet hyperboloid. So imagine this thing opening towards the top and the bottom, but because the y is negative, which the y is the only different one compared to the x's and z's, which way is this going to be opening? Right? So it should be opening along the y-axis, positive and negative y-axis. Whew. So I can graph both of them. If that looks a little too confusing, I can eliminate this graph. I just, how do I eliminate? Oh, remove. So now I have this thing opening along the y-axis like we were saying. Okay? You can color them. You can control the color somehow. I don't know how exactly. Oh, and if you have 3D glasses, you can view this in 3D. Yeah, you need the red and blue 3D glasses. Yeah. I meant to buy a stack of glasses for this class. I forgot. All right. So that's the story with this. I encourage you to mess around, type in a few things. Oh, by the way, the cone that we have, z squared is equal to x squared plus y squared. It's hard to visualize. Actually, let's graph it again. We don't have anything in our notes yet, so let's put this in our notes. Yeah, so advantages and disadvantages. Obviously, the advantage is that you get to see nice pictures with this, but disadvantage is that this is still a machine that's doing a command, and it doesn't follow the infinitesimal calculus that we do, or even just the plotting. And so they're approximating, and so they technically, yes, it is supposed to be touching the origin. But because of the way the thing is being plotted, it's not enough points to see that. So this is a 3D plotter, calc plotter. I'll try to remember to put the website, but this is our example of a cone. What? I don't know. It's funded through a grant through the NSF. I don't know if that is an open source thing that you want to mess up. So the other point I was trying to make here is that this is x squared plus y squared is equal to z squared. If I were to solve for z by itself, I would need to take the square root of both sides. And if I were to take the square root of both sides, I'm going to lose one of the sides because the square root will have a positive and negative side. So if I'm willing to lose, let's say, the bottom part, and I just consider the square root of x squared plus y squared, then I can get the top half of the cone. Notice now that this doesn't look like my other cone. My other cone looked a little nicer, actually looked like a cone. This looked like a square piece of paper that got folded. That's because it actually is a square piece of paper that got folded. And that's dependent on your domain. We talked a little bit about that, the domain business. And if I fiddle around with my domain, these are my domain values for the x, y, and the z. Then I can possibly change the way this looks. But if you compare it to the other graph, now it's kind of bleeding in together. There's a way to control this. I know there is. There's a color option. Well, maybe you guys can look for it. But my big push is for you to mess around with this. So yeah, so there's a color option. There's also ways to trace things around. You see the dot? That is tracing around the function, because the function is defined that way. All right. So we'll come back to this today, but I just wanted to introduce you to the 3D plotter. Our main focus today is starting on Chapter 13. Oh, the other thing I have here is a game that you could play. Idea is to memorize the graph and relate it with the function and the name. So I have equations and names and graphs. So maybe you could shuffle it around, turn it upside down, and try to see if you could play a matching game for matching the quadratic sections. And it would be good to be able to look at an equation and be able to tell what kind of shape it is. All right. If you're a computer science major and have done a matching game before, maybe you can write a program that would play a matching game. All right, vector valued functions. So we actually know these functions already, except now we're going to, this is essentially parametric functions, parametric equations, except they're going to be brought up to 3 dimensions. So if you remember the line, What do you need for an equation of a line? Point and direction. So for a line, you need a point and a direction. Remember, the rest of the semester, when I ask what do you need for an equation of a line, this is what I want to hear. Okay, what do you need for an equation of a plane? Normal. Point and normal. So you need a point and a direction, and then so your point, let's say your point is I think we use x naught, y naught, z naught, and then your direction is, well, let's make it generic, d1, d2, d3. And so your equation of a line can be written in what we would call vector form. We would generally write it as a point plus t times a direction if we assume that the point is a vector. And then what you could do is you could break this up into the different components of the point. So, and the point and the direction. So it's going to be the x naught, scalar value x naught plus d1 times t, comma, y naught plus d2 times t plus z naught d3 t. So this is a vector form of the line, and then we could easily change that into parametric form, right? And in parametric form, you essentially just take each of those separately. And then you would put them with the generic variables x, y, z, and they would end up being dependent on t. And so that's your parametric equations. So these vector valued functions would just be essentially a function in the x component, a function in the y component, and a function in the z component that would draw something in space. So now the interesting question is, what is it going to draw? Is it going to be a surface in space? Or is it going to be a curve in space? What do you guys think? Surface or curve? Let me ask the question, let me rephrase the question. Is it a one-dimensional curve or a two-dimensional surface in three-dimensional space? Any ideas? Yeah, so this thing has one parameter t. That one parameter is going to dictate how many dimensions you're going to go into. So the one parameter t will tell us that at each value of t, you're going to get a point, and then you can just plot some of those points and then connect it together, and then it'll be a one-dimensional object. In this case, we're in R3. There's 3 components, so it's a one-dimensional object in 3D. So this is sometimes called a space curve. Yeah.
Have a function of t for every direction plotted in, right? So otherwise, f of ti hat plus h of t k hat, and then you still have a plan.
you'd still have a curve, but that curve would be restricted on a plane. Yeah? Okay. So let's take a look at some examples. And probably the most popular example for any first example of this is this graph. So we generally use R to represent a curve, and then it's a vector-valued function, so it's a vector curve, so that has an arrow on top. And t is your parameter, and t is just a scalar. So this is equal to cosine of t in the x, sine of t in the y, and then t. Sometimes we scale this, multiply it by like a half or something so that we can get a nicer picture. So I'm going to put 1/2 here. Now let's imagine how this thing looks like, because that's part of what we want to do, is we want to look at a curve, and if it's manageable enough, we could try to imagine how this thing might look like before we actually go on a computer and draw it out. So if you imagine how this thing looks like, in 2 dimensions, we see a circle. So whatever is being drawn looks like in the x and the y, it's going to go around in a circle. What's happening to the z? It's getting larger, right? Imagine, close your eyes, imagine. Along the x and the y, you're just going around in a circle, but in the z, you're starting to increase. And you're just drawing a space curve. You're just drawing a curve in 3 dimensions. What are you drawing? Spiral. Slinky. Spring. Anybody know what that's called? Helix. You're drawing a helix. Idea is that if you look straight down, all you're going to see is an image on x, y, z is a circle, cosine t, sine t. But then if you switch your view to look at it from a different angle, you'll see that it's going up. Now, depending on what t is equal to, you could go down as well if you put negative values for t. But in general, it's a spring, so this is a helix. So the 3D plotter that now I'm trying to plug, because it's free, D plotter. So let's clear the graphs again. Let's get rid of that stuff. And let's take a look at a graph. And one of the options that you have here is space curve. So let's add a space curve. And a space curve is kind of written in parametric form. You see how popular the helix is. It's already up there. The cosine t, sine t is the default. And then t here is being multiplied by something else. And our t goes from -10 to 10. Let's have it start with 0, and then we'll play around with these things as we go along. Maybe the 1/10 would have probably worked a little bit better for us, though. Because the 1/2 brings it up there a little faster than I'd like. That's a little bit more viewable. So if you look at it from the top view again, these are the circles that I was talking about. All you see is a circle. And if you look at it from a side view, then you see the z values go up. All right, reset. Now the neat thing about this is that I can trace different values. So the values that we're going here, it looks like we're going from t is equal to 1 to 10. So let's just put t is equal to 1 to trace it, to see where it might go, might be. Can I trace? There it goes. I have to animate maybe. Well, animating would be more fun anyways. So let's start with t is equal to 0 and animate. As you can see, as the t value changes, the point is on a particular spot on the curve, and what this is doing is it's telling you how it's drawing this particular curve. The number of steps tell you, this is a computer thing, it tells you how many dots to plot, and then it's going to connect the lines. So the more you have, the better it's going to be, but the longer it might take depending on how complicated your curve or your surface is. So if we do this in, what is it, pi over, we're going to 10. Let's do this in 10 steps. If you cut it down to 10, you start losing that smooth curve look, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if you cut the number of steps to like 5, then it doesn't really even look like a helix anymore. So the idea is that the larger you have, the nicer, the smoother it's going to look like. Use constant primary colors. There you go. All right. Any questions? So we could come up with more examples. And usually things with the sine and cosines are nice because you can, they're kind of restricted. It's a periodic function, so it stays kind of restricted to whatever the area is. So let's do another one with a sine and cosine function, and then I'll have you guys think about how this might work out. So sine t, cosine t, but this time I'm going to have another oscillating function, and then I'll change the period for this one. Just to make it interesting. Now let's think about it again. Keep imagining, I want you guys to work in groups and stuff. So talk about it with somebody next to you and try to see what this graph is going to look like. I'll give you 1 minute. I saw some people talking to each other. That was cool. I'm going to force you guys one of these days. Actually work with each other. Yeah?
There is a game called Visit Live where you can actually collaborate, where classmates can actually collaborate with each other in teams and compete.
I don't want to make it a competition.
No, make it a
'Cause- Well, the thing is that the point isn't to make a competition to have somebody be a winner, because we're all winners here. So what I want to do is I just want the interaction business. So, I mean, maybe we'll try it. What's it called? Quizlet. I've heard of that. Yeah. I meant to prepare some Flickr questions for you guys too today. Maybe tomorrow we'll have some questions about maybe this stuff. All right. So the idea is that the x and y are still going to be restricted to the circle if you look at it from the top. But the z now oscillates. It's going to oscillate a little bit more. It's not just like the previous example, the z just went up. This one goes between 0 and, well, actually goes between -1 and 1. So your z height of your curve will never go past that. So what you could do for this to try to imagine this is imagine this particular graph over here, the sine 4t. Imagine wrapping that around into a circle. And that's how it's going to look like. So let's see if we can graph that here, and I'll just get rid of the other graph. So it's like taking that sine curve that has, you know, we've compressed the sine curve so that it has a period of, what is it, pi over 4 or something like that, or maybe pi over 2. And then we're asking it to go around in the x and y in a circular motion. So if you follow the animation of how this is being traced, maybe slower. Can I make it slower? I don't know if that does. That doesn't go slower.
Or can you drag it? Yeah, you can use the
Oh.
slider to manually do it.
Yeah,
There we go.
cool. All right, so this is starting with 0, t is equal to 0. And then you see it going up and down. If you look at it from the top, it's just essentially tracing out that circle. I know, because I don't have it exactly up on top. Yeah. It's supposed to be a circle.
That looks about like my circle.
Can you set the period in z to 1 as opposed to 4?
Yeah, what do you think will happen if I set the period to 1? So it'll start, and then it'll finish its thing by the time it gets to 1. So it'll be a simpler looking graph.
Whoa. Whoa.
But it's lopsided.
Well, it's essentially it follows the circular motion along the z. So it starts. So this thing goes all the way up to 10. Let's just go to, what is it? 6. What's 2 pi? 6.28. Oh, I don't know. So if we trace this, reset graph. So if we trace this, we'll see that the z component it only has one cycle. It goes up and back down and back up again, and so that's one whole loop. And so it just draws that from the z component, it look like it's actually drawn that circle. So if we double that, so this thing, I don't know if you guys notice, what does it look like? A Pringle? A saddle. Looks like a Pringle or a saddle. So this, we'll see later on, that has some relationship with what's that shape of a saddle that we talked about? Hyperbolic paraboloid. Yeah. Hyperbolic paraboloid. So let's put that 4 back in there, and then that'll be our picture for our notes. Well, the double helix, if you look at the double helix, that's 2 helices. Helixes. So, and then they're connected by those letters. What are they called? Anybody a bio major?
The nucleotides.
The A matches with an A, and then the G starts with a T.
Yeah.
There's one of them that matches with something that's not the same letter. Anyways, so a double helix is 2 helices. With some bridges between them. Okay. So the thing is that you'd see all kinds of other examples, like maybe from your homework. Oh, we need to go to so you'd just be asked to match, in this case, match the function with the correct graph. So for these problems, what I'd ask you to do is try to look at it and try to reason with it. So we got the t cosine and the t sine. So it looks like it's going around in a circle, but the t makes the radius wider. So it looks like it's going to be spiraling on the x and the z-axis. And then in the y-axis, you just have a t. So it looks like along the y, it's going up. So if you could picture that, then that's great. Then you can select one of these. But if you can't, I suggest that you just type this into the graphing plotter, 3D plotter graphing thing program, and then see what you can get out of it. Okay? All right. So let's move on. So the next step is this is another tool that we've learned about vectors and parametric equations, and now vector functions is essentially a parametric equation turned into a vector. So that's all it is. So we're just kind of accumulating these tools. And we're in calculus, so we should do some calculus on these things. And we'll start, well, there's an idea of a limit here too. I'm not going to talk much about limits. I think there's one problem in your homework to deal with limits, but really it's just, putting in those values, the t values, and getting out whatever you get out. So let's focus more on the derivative and the integral of vector-valued functions. So the derivative is fairly simple. It's defined by this, which I don't know if you guys remember, unless you're a tutor for Calc 1. This stuff probably went in your head and out by the time you get past Calc 1, which is fine. It's essentially, yeah, the difference quotient. And there's some nice geometry behind this, analytic geometry behind this difference quotient. But really, the bottom line is that the derivative of a vector-valued function is essentially taking the derivative of each of the components. And that's the bottom line. That's what we're going to focus on. Yes, it's still a vector because when you take the derivative, you just, each of these things, it'll still be a vector function, which means you can't really call it an official vector unless you put in values for t in there, because otherwise you don't know where it's pointing. So for this, let's I was going to say, let's take an example in 2 dimensions. And then we'll bring it up to 3D. Now let's just take an example in 3 dimensions. What the heck? We got that cool program anyways, right? So let's do an example of taking a derivative. And, after the derivative, that's not really the important part. The important part is what do you want to do with that derivative. So this is the application portion. So let's take our helix example. Our helix example was the cosine and sine. Should we go 1/2 or 1/10 if we want to picture it? Let's go with 1/10. And let's just go ahead and take the derivative of this thing. And when you take the derivative, it's component-wise derivative, so component by component. Derivative of cosine is negative sine. Derivative of sine is positive cosine. And then the derivative of a constant times a variable is just whatever that constant is. So the interesting thing is to ask is what is this now? So Frederick asked if it was a vector. Yes, it is a vector. So it's a vector function at this point. That's a vector. Let's find out what's happening at 0. Let's say when t is equal to 0. So when t is equal to 0, your r, the original r, and I want you to really pay special attention to the way the arrows and the primes and where they are and stuff like that is happening. So here r, this is the original function, r, and we're putting 0 in for r. So what's the cosine of 0? Sine of 0, and then 0. So this is the original function, r of t, and then I put 0 in there, and then this has a special meaning. This is a vector. Now it's clearly a vector, and it has a special meaning for us for this graph. And anybody know what the special meaning is? It's what? Special meaning, what is it in terms of the graph that we were looking at? No. This is a vector, but what about this vector? I think you're there, but okay, stop. We can think about it as a starting point, yeah. But this is a vector. Essentially, what this vector is let's see if I can draw my vectors here. It's from the origin, and it's pointing to wherever this point is on the graph. So And sometimes we tend to call this the position vector, because it's the vector now from the origin, which means it's in standard position, and it's pointing to the current position on the particular curve. Yeah?
And the derivative is the direction.
The derivative will be the direction, but we'll take a look at that and see what that really means here. So let's take a look at that derivative, and again, we'll put t is equal to 0 into that derivative. So now I have r prime of 0 to denote that this is the derivative of the r function, and then I'm putting 0 in there. So I need to take the derivative of the r function. We already did that. And let's put 0 in there. You get 0, 1, 1/10. So 0, 1, and 1/10. Now if I draw that, how am I going to draw that? Let's try. So 0 in the x, 1 in the y, and then 1/10 is a small little lift. Like this. So I think, does it point towards another point on the curve? The answer is not necessarily. It might have been in this case, but if it is happening in this case, it's coincidental that it's pointing to that point on the curve. So the vector that comes from the derivative is actually not very meaningful in standard position if we let it sit at the origin, because it's associated with a specific point on the graph. And so what would be more meaningful is that if we take this vector, move it away from the origin, and maybe put its tail at the actual point on the curve. So when we do that, it has a little bit more graphical meaning, doesn't it? Does it look like it has more graphical meaning? Does this vector look special now? Yeah. So this vector happens to be tangent to the curve. If you take the derivative of the point and put in an actual t value, and then you move it to that position, then you have a vector that's actually tangent to the curve. Okay? So that's what's really cool about this, the derivative. It kind of becomes built in as a tangent vector. Okay? So I want to be careful calling r prime of t the tangent vector, because technically this is a vector function. Just like in Calc 1, when you have, like, for example, t squared, the function t squared, that's a parabola. And then when you take the derivative of that is 2t, right? So we don't think of 2t as the slope. It's a slope for the graph in general, but it's not the slope at specific points. And so that's what people tend to forget a lot in Calc 2 or Calc 1. I'll put a recall here. If you have y is equal to x squared and y prime is equal to 2x, and then you want to find the equation of a line, of the tangent line, at x is equal to 1, for example. So you put 1 in for x to get your y value, and then you get 1 for that. So your equation is not y is equal to, or y minus y1 is equal to the slope times x minus x1. So what people tend to do incorrectly is they put the whole derivative function in there. But that's not correct, right? If you graph this, this isn't even a line, much less a tangent line. But if you graph this, you'll see it's some sort of parabola thing that's not going to match with whatever it is you're doing. So be careful with this. And the point, I think when Frederick asked if this is a vector, I wanted to say yes, it's a vector, but no, it's a vector function. If you want an actual vector, you need to plug in the values for t, whether that be t is equal to 0 or whatever else you need it to be. So the point is that you need to evaluate your derivative at a specific point. So that it would match the slope of the line that you're talking about. So if you don't do that, if you don't put in the value into the derivative, then it's just going to remain a vector function. So in fact, I still got a couple of mistakes here. I think it was one of maybe your first quiz when I asked for the equation of the tangent line for the parametric equation. Some people didn't evaluate this at a particular point. So be careful with that. It's a common mistake. Okay? So that's your tangent vector. And, you know, we could do more derivatives. So, by the way, the tangent vector, sometimes, well, let's put names to that a little bit later. Let's put names to it right now. Sometimes it's called a position function. And so this is not the tangent function. Sometimes it's called the velocity. So the tangent vector and the velocity vector turn out to be, if you want to call it a vector, this can also be called the velocity vector. So back in calculus 1, maybe 2, you guys have dealt with velocities and accelerations and stuff. And so the velocity that you guys found were just scalars. And maybe they're positive to say they're going up and negative to say they're going down. So because they're scalars, you guys are only able to study motion in one dimension, the height going up and down. But now we could talk about this in 2 dimensions or even 3 dimensions. We could talk about the velocity of the ball actually not just going up and down, but moving somewhere in space. So it has an x, a y, and a z direction that it's moving in, unless the velocity is 0 in one of those directions, then it may not be moving in that particular direction. But in general now, we could talk about velocities as a vector to describe motion in more than one direction. And so you can guess what happens if we take another derivative, r double prime of t is called the acceleration. Function. And then once you drop in a value for t, then we can call it an acceleration vector that's specific to a particular value. And so sometimes they call this A, and sometimes they call this velocity V with an arrow on top. Right. No, it's a derivative. Yeah. But we will be integrating, like it or not. What? Oh, not yet. That's not. This is just kid stuff integrating. We'll get to the adult section later. Wait, that didn't sound right. So let's finish this thought about the acceleration. Let's take the actual acceleration function here, which is the derivative of the velocity. So the derivative is going to be negative cosine t, negative sine t, and take the derivative of that, you get 0. So let's think about that for this particular problem. Negative cosine, let's put 0 in. R double prime of 0, which means I want to find the acceleration vector at 0. So cosine of 0 is 1, but there's a negative outside, and then a 0 for the sine and a 0. So you have negative 1, 0, 0. So again, we have a vector from the origin that doesn't go up in height in z, but it looks like it's pointing in the exact opposite side. If I put this in a standard position where the tail's at the origin, this is how it would look like. But again, it's not going to be that helpful unless I move this to the actual, move the tail to the actual position. And if I do that, it looks like the acceleration for this helix, for this particular helix problem, is going inward. And does that make sense for you physics people? You're going in a circular motion, right? So the acceleration is always pulling you in. Centrifugal.
Well, centrifugal and different, actually.
All right, so we'll do this a bunch of times. You guys will be experts with the velocity and acceleration vector. And then next week when we work in groups, you guys will no.